Welcome. I'm looking forward to this presentation because I have a lot of things I want to talk to you about. So let's just get started. My name is Alex Theedom, and my main role is developer, but also I'm an author. I authored this book, Java E Design Patterns, with Murat Yener. Many of you may know him. And it's a nod here at the front. Anybody has bought this book? Anybody downloaded this book? Okay. Doesn't matter, it's fine. But also I do some training. I do training online for lynda.com, Enterprise Edition training. It's very simple, basic introductory level. So if in your businesses, for example, you have new recruits who need to get up to speed very quickly on Enterprise, you might want to consider providing them with some online training at a very reasonable cost. Also, I have a blog, and from time to time, when I have time, I will publish articles that about essentially Java Enterprise Edition on my readlearncode.com blog, and I talk at conferences from time to time as well. So, what's on? I'm going to tell you a little bit about what we're going to be talking about so you can decide whether you want to leave or not. Okay, so this is your chance. All right? So first of all, I want to talk about why we need HTTP2. What is the motivation for HTTP2? And really, the motivations are because there are a number of workarounds. We've had to develop workarounds in HTTP 1.1 in order to compensate for various shortcomings, which we'll have a look at in detail later, because those shortcomings give us the motivation for HTTP2. I'm going to have a look at sockets. Sockets are important, and there's a distinct change between version 1 and version 2. And I'm going to have a look at just the top line features. There's a lot of stuff going on in HTTP2. I mean, I'm going to try and cover as much as possible. If I talk too quickly, I apologize, but that's only because I want to cram in as much as possible. I will try and keep it reasonably succinct. Then I'm going to have a look at what this means in Servlet 4.0. Okay, now there are some things you need to be aware of, some things you need to know, and it's useful to know how this actually, this change in the HTTP protocol actually translates to real life. You know, what does this mean for you when you're developing servlets? Then I'm going to have a look at what servers actually support HTTP2, or more important, what servers actually support the latest edition of Enterprise Edition 8. Have a quick look at the status update. Always good to know where we are with the JSR. If we have time, there's a little bit extra bits I've thrown in. The slides will be up on the internet by the end of the day, so you'll be able to find where they are, and I'll tweet them as well, so you can see them. And then at the end, any questions and answers? Well, questions and answers. So, what's the motivation for HTTP2? Well, when we started the internet, when we started at the very beginning, we had a very limited usage for HTTP, and its usage has changed quite substantially over time. And that has resulted in a reduction in performance. Now, we all know how important performance is from the point of view of a customer. You know, milliseconds makes a difference between transactions. You must give the rich user experience that the users have now come to expect. And doing so, using HTTP 1.1 has become a challenge. You know. And we've done a pretty good job of dealing with that challenge, but now it's time for change. So a website used to look like this. So back in the day, this is what the BBC website looked like. Very simple page, okay? A couple of images, a few text links, nothing to it. But this is what it looked like this morning, okay? Images, graphics, CSS, you can imagine what's going on behind there, okay? You've got JavaScript, you've got all kinds of stuff running behind this website to make this work. And a lot of resources that are downloaded in order to make this page the kind of dynamic experience that we want. So what this means is that the HTTP protocol, as we know it, is not really suitable for modern use. It's not really suitable for what we want to use the internet for. It doesn't really satisfy our requirements. And we'll have a look at the reasons why as we go through this presentation. And this is really because the average size of web pages has increased substantially. They include an incredible amount of resources, increased by 300% in the last few years alone, and this is from the HTTP archive. And that's the problem. HTTP 1.1 can't handle it. It can't deliver the kind of resources in the way that we want to deliver the resources. And we've had to develop a number of workarounds. But how did we get to this position? Well, first of all, the HTTP 1 requests resources in parallel. It requests one resource, then it requests another resource, and then another resource. And so it uses one request per TCP connection. It's not very efficient at all. But when you've only got one or two resources, it doesn't really matter, it's fine. When you've got several hundred resources, that's when it becomes a problem. So in HTTP 1.1, they developed HTTP pipelining. Pipelining really allows you to make various requests over a single connection. Now this is a good solution, okay? This is fine. It responds in sequence, so you request a page, and it responds as each one is available. The problem with this is what happens if one of these resources takes time to come back. You're blocked, okay? You're stuck. And this delay is called the head of line blocking issue. And one of the big issues that actually HTTP 2 sets out to resolve. And we'll see that later on in the presentation. So what are the workarounds? I'm going to talk about the workarounds because these are the motivations for HTTP 2, and because many of the applications that you may be working on have these workarounds already there. And with HTTP 2, you don't need them anymore. So what do? We'll answer that question later. So, we have a situation where we want to create multiple connections. Okay? We want to create multiple connections in order to download all of our resources. So we create one connection that downloads our style sheet. We create another connection that downloads our JavaScript. And we create another connection that downloads our image. Okay, that's fine. But creating a TCP connection is very, very expensive. This works fine, but there are issues. The issues are that it is expensive. It's expensive to create a TCP connection for every resource. And if you have to create several hundred, or even tens of these connections, that's pretty heavy work. So as I said, it's expensive to do so. And the browser has a limit to the maximum number of connections that you can make. Now, the connections are not necessarily specified in any particular specification. As far as I know, the HTTP 1.1 specification does not specify exactly how many connections a browser can open. It's just by convention. So how do we get around this issue? So one of the workarounds is to concatenate all of your CSS and JavaScripts together. And so you would have, imagine 3 of these CSS files and concatenate them together to one great big fat style sheet. Okay, that works. You've got one connection instead of 3 connections. But really, is that how you want to design your sites? No, that's not how modern design is done. Modern design is about separation of all the things as much as possible. So you have separate style sheets. Another workaround was to inline your JavaScript. So you would actually write a JavaScript inside your HTML. Again, this works, but again, it's not really a great solution because you are mixing functionality, you're mixing style with form, and it's just not how we really want to design our website. We want to separate out our concerns. It worked, but again, it is a workaround. A workaround because of the limitations of HTTP 1.1. Images, for example, can be inlined as well. And this is a specific example, a specific case of inlining, where you take your image and you encode it, basically encode it, and you'd actually copy and paste the entire code directly into your HTML file. Again, you are reducing the number of TCP connections, great. But again, you are mixing, your images in with the actual HTTP code, HTML code. Again, not really a great design pattern at all. And of course, you have this issue when you have to decode it. It takes a little bit of time. It's a little bit expensive to decode it. And caching is just impossible. It's just very, very difficult to cache properly. So, An alternative is to have a style sheet, to have a sprite sheet. You have all the images on one single piece or one single page, as it were, one single image, and you use JavaScript to cut up your images into little sprites. This works really great, and as you can see, these are some real-life examples of companies that actually use it. So Amazon uses it, and I think that's excuse me, Facebook and Google. They all use this technique, and it works very well. But again, you're having to process on the client side images using other techniques, and again, it's a workaround. It's another workaround. Domain sharding, again, a great solution. Works very well, but you need several domains. And the object of this is to get around the maximum number of connections that a browser can make to a particular domain. So if the maximum number is 5 and you need to make 10 connections, then 2 servers are necessary in order to make that number of connections concurrently and in parallel. It's a really good solution. Works, but again, you're designing your back end to overcome more issues with HTTP 1.1. So really, when you see workarounds, what you should be saying to yourself, well, actually, the technology I'm using isn't really up to the job. It's time to make a change. It's time to look at something new, and that's really what pushed the need for a rethink of the whole way that the HTTP protocol works. So let's have a look at sockets. Sockets are important. I've mentioned sockets a number of times, and that seems to be, from what we've seen, the reason why we have a number of problems. Sockets are expensive to create. So what does the HTTP 1.1 spec say about sockets? Not an awful lot. It's not very vocal. It's not very explicit on what it wants you to do with sockets. I guess it's probably because it never imagined that you want to open more than one socket. Why do you want more than one socket if all your page is just one single HTML page with one image on it? You just need one socket. So I would imagine that was the thinking. And it kind of implies that it's a throwaway resource. You can create a TCP socket, throw it away. Create another one, throw it away. We don't need to maintain these sockets open. And it doesn't, like I said before, it doesn't specify a maximum number of sockets. So it's very, very silent on how to deal with sockets. Now this is in contrast to what HTTP 2 says about sockets. It talks about sockets a lot. It's recognized that there was an issue, that the number of sockets does matter, and that something should be said about it. So it specifies what should be done with regard to sockets. And what it says is that sockets should be treated as a scarce resource. Okay? Sockets are precious, and you do not open all the sockets you can. You do not use sockets in any other way than simply trying to open just one socket and trying to do everything over one socket. And that is what HTTP 2 does. It creates one socket, or ideally one socket, and everything happens over just one TCP socket. So you go from a situation like this, where you have many open TCP sockets, to a situation like this, where you just have one. So let's move on and have a look at the top-line features of HTTP 2. And these are the principal features. These are the ones that are most important and the most interesting, in my opinion. So HTTP 2 consists of 2 specifications. Okay? One specification talks about the actual protocol itself. So if you want to do that, it's RFC 7540. And HPAC is another specification. This is about header compression and how headers are compressed within HTTP communication. And this is RFC 7541. So if you are suffering from insomnia, there's your solution. But download those and have a good read. No, but seriously, they are actually worth reading. And later on in this presentation, what I will do is I'll put up a slide with some really good links to some excellent online resources that really go deep into explaining how this works. You don't have to read the specifications, you can read somebody else's interpretation of them. And it's a binary protocol. Okay? Now this is a big difference. This is a massive quantum shift from where we were before with HTTP 1.1. 1.1 is text-based. Two, it is binary. It's binary because it's based upon frames. Now, frames is a concept which we'll be looking into a little bit deeper later on in this presentation. And it's a concept that is borrowed from networking. So those of you who are familiar with the structure of how things are worked within the networking concept, they've borrowed the concepts from there and have implemented them here. So you'll see something that is very familiar when I go through the next couple of slides. So, what is this all about? Well, the Topline feature, the most important feature in terms of delivering performance, is the request-response multiplexing. So what do we mean by this? Well, what this means is that we are able to multiplex our communication bidirectionally across a TCP socket. Okay, and we'll see a little bit more of this later on. These are just headline features. Binary framing. Okay, binary framing is about breaking down the TCP connection into smaller component parts, which we call frames. Again, we'll have a look at that in more detail later. Header compression. Header compression is about removing duplicates in the HTTP header. Okay? Now there are lots of duplicates in the header, and we'll see examples of this later on. Stream prioritization. Okay, this won't make much sense at the moment. Basically, you can give priority to certain streams or certain resources, essentially. So certain resources are more important than other resources and should be delivered first or delivered sooner. And we'll have one slide on this later and have a look at that then. And server push. Okay, this is the one that actually we see implemented in the Servlet 4.0 specification, and we'll have a look at some code on this later. Okay, and this is a particularly interesting feature which I'll talk about. There's several slides on this later on. So, the most important features. Request and response, as I've just mentioned, and this resolves the need to open up multiple TCP connections, because everything can be multiplexed bidirectionally over a single TCP socket. If you have one socket, everything goes backwards and forwards over this one single socket. So before I move on, I just want to define a couple of concepts that I want to talk about over the next couple of slides. So a connection, when I talk about a connection, I talk about a TCP socket. Okay, a connection is a socket. Over a connection, you have a stream. A stream is a way of communicating over that particular connection. Now, within that stream, you will have messages. Messages are the request and response that we're used to, the familiar request and response that we know when we talk about HTTP, we talk about request and response. That's what this is. The messages are the request and response. It's a logical representation of those messages. Also, we have control messages, and I'll talk about what those control messages are as well. Control messages are for the browser or for the server, giving instructions on what to do, what not to do, and so on and so forth. We'll have a look at examples of those later. Frames are the smallest part of the communication. It's broken down even further to the smallest possible component. And again, we'll have a look at this in more detail, but this is the smallest component. And this might look quite familiar. Let me just move on to this one. This is a visual representation of what I've just spoken about. Okay, so for those of you, like myself, who like to see things in pictures, this is a really good way of explaining this. So you've got one big connection, okay, one big socket being opened, and within that socket, you've got streams. And then within those streams, you've got messages, and then within those messages you've got frames, and that's how it's broken down. And we're going to be looking at those components over the next couple of slides before we get to the server implementation. So, how do you visualize a stream? How do you visualize a connection? So you've got this interlacing of messages, interlacing of what are essentially frames over a single connection. And how does this interlacing work? It works by breaking up a request into its component parts. So you have a request which is broken up into headers and then body. And even that will be broken up further into smaller frames and sent separately. Okay? You don't send the entire request or the entire response in one unit. You're breaking it up into its smaller component parts and then reassembling it, essentially, on the other end, either the server side or the client side. And this all happens transparently. You know, the server does this, the client does this. You don't need to necessarily write code that reassembles the messages, but understanding how it works and why it works is absolutely essential, of course. So here we have a situation where stream 3 sends its headers first, then later it sends its data, which is its HTTP request body. Okay? And before the server receives the completed stream, it sends back the response to stream 2. So we're not waiting for anything. Okay, so this is why the head of line blocking issue is resolved, is we're not waiting for any particular resource. We're not really waiting for anything. Resources are broken up and sent in bits and parts. So let's go down a little bit deeper and have a look at a frame. Now this is important to decompose a frame because parts of what happens within a frame actually do matter in relation to what code you might be writing at the servlet level. And having some understanding of what's going on here is actually quite useful. And the things that are worth paying attention to are the type, the flags, the stream identifier, and the frame payload. Okay? So every single frame, remember this is the smallest part of the communication, contains fields of type headers. So headers, data, push promise, RST stream, priority, and the various other ones. And if the type, for example, is a header, then it means that the frame payload contains header information. If the type is data, it means the frame payload contains data, the actual data you want to send, the JSON response, for example, if you're sending JSON data, for example. A push promise is a special type of frame that is like a special type of frame that is sent by the server to the client and is a promise, or I guess you could almost say like a request to the client being the browser, to send a resource. So the server sends notification or request for permission, however you want to perceive it, to the client saying, I want to send you this resource. The resource could be an image, it could be a CSS, it could be something like that. Okay? That's what a push promise is. This is important because later we'll have a look at this. RTS stream is the client's reaction. Oops, sorry, went too far. The RTS stream type is the client's response. And the client is saying to the server, no, I don't want that resource. Don't send me that resource. I already have it in my cache. Okay? I already have this resource in my cache. Don't send it to me again. And this is a very subtle thing, but actually, when you think about it, when you're reloading a web page or when you're revisiting the same site, you don't have to then download the same resource again. Okay? And this makes a big efficiency saving in many ways, okay? On both the server and the client side. And because these frames are very, very lightweight, they weigh virtually nothing. It costs nothing to send these push promises and to respond. Okay? Much less than sending a resource that the client doesn't need or doesn't want. So let's decompose what a traditional HTTP request looks like and put it into frames. So here on the right of the screen, we have a traditional HTTP request to an index.html file. Okay, and you can see you've got the simple GET request, you can see the file name, the file path, you can see the protocol, it's got the host name, it's got the type it accepts. Okay, on the other side of the screen, on the left side of the screen, yeah, depending which side you're on the other side of the screen, on my left, on your right, you can see how that HTTP request is broken down. Okay, now it's broken down into a frame of type headers. Okay, so remember back to the previous slide. This is what a frame looks like. So the type is headers. The end stream and end headers, they are configuration flags. So in the previous slide, you can probably go back. So in the previous slide, you've got flags, okay? They're configuration flags. That's what these end stream and end headers flags are. A minus means this is not the end of the stream. So this is not the last frame in the stream. And a plus means this is the end of the headers frame. Okay. And then we have the sort of pseudo HTTP headers, get HTTP, and you see they map directly to what we're familiar with in HTTP 1.1. Let's have a look at the other side. Let's have a look at the response to that request. So the response traditionally would look something like this. You've got a 200 OK response, you've got the length, you've got the content type, and you've got the payload, may the force be with you. And what you have is this response is broken up into two frames. Okay, you have two frames. You have a header frame, which describes the headers, and then you have a data frame, which describes the data. And they're sent separately. They're sent separately so they can be interlaced with other responses. So you're not only going to be requesting the HTTP index page, you're also going to be requesting lots of other stuff as well. All kinds of other resources perhaps are also being requested at the same time. So the server wants to be able to break up the response, send the response in bits. As that part of the response becomes available, it will send that part of the response. So again here, you have the type is frame. So the frame type is headers, because this is a header frame. Is this the end of the header? Yes, it is, because it's positive. The plus sign means it's positive. This is how we're representing it. And here, the data stream, we have a positive value specified for the end stream. So this is the end of the actual stream for this particular request. So the client knows that this is the last frame for this response. Therefore, it can complete that particular package of transactions, where that particular request has come back in total. But you'll notice with that there's still a problem. The problem is you've got duplication between requests and response. Okay, you have a request which contains a lot of header information. You also have a response to that request which also contains a lot of header information. And as you'll notice, it's duplicated. There's a lot of duplication there. The method is the same, the schema is the same, you've got the host is the same. Everything is really basically the same between request, response, between different requests. Okay? So you're making the same requests to the same server, and you're going to be making lots of different requests, and they have more or less the same kind of information. So what happens is that we have HPAC, which compresses this and attempts to compress the header, and it does this by keeping a delta of the differences between requests. Okay? So the first request is going to look like this. It has all the headers in it. Now the second request is going to look like this. It just has what is different. Now as you can see, okay. So yes, it reduces substantially to just the path. And that is the implementation of HPAC and how HPAC compresses headers by removing duplicates and only sending the deltas. Stream prioritization can be specified. That allows you to specify one stream is more important than another. A server can completely ignore that priority if it wants to. It doesn't have to respect it. It's just a suggestion to the server. Okay. So this eliminates the need for inline resourcing completely. Okay. So the server can now proactively send some resources to the client. This is what Server Push is about. Okay. And I want to move on to this particular topic because I think this is actually quite interesting. And so Server Push is about analyzing what resources a client needs before finishing the request, before responding. So you make a request for an HTML page, and that HTML page contains images, it contains the CSS, and the server analyzes that and sends those resources to the client before it's actually finished processing whatever business logic happens to be in your servlet or your index page. Okay? And then it sends back the HTML page as processed. Like I mentioned before, a client the browser can reject a push promise. So if it already has that image, if it already has that CSS in its cache, it can send a rejection, an RST stream rejection, to the server for that particular resource. So in the servlet features, now the most visible improvement in servlets is going to be in this particular location. It's going to be in the way that it implements HTTP2, and particularly in server push. Now, servlets are the best place for this, because this is where we actually are communicating. This is where our web applications are constructed. And this is kind of what it looks like. The way this works is that to use the push server, within a servlet, you obtain a reference to the push builder from the HTTP servlet request, and then you mutate the builder as desired, and then you call the push method. So that's the code implementation of server push. So let's have a look at how this works in terms of a sequence diagram. So the browser requests an HTML page, the server analyzes the page and discovers that it contains various resources. You get the push builder, and you then start setting the path of the CSS, and you invoke the push. You set the path of the JS, and you invoke push, which pushes those resources, and then you respond with the final response to the HTTP request for the index page. So, how is this constructed? A little bit more detail. So essentially you have a situation where the builder, this builds a push request based upon the HTTP service request from which this build is obtained. Okay, it obtained it from here. The push request is constructed with the request method set to get as a default because it can't mutate. Push is not allowed to make any change to any state. And various values, conditional range, etc. These are all removed. They're stripped out. Cookies are also removed, but only added if the max age has not expired. Okay. And there are various other details. The only required specification, the only required thing that you need to set is the URI of the actual resource you're going to be pushing. Okay. And then that must be set before you call the push. So very simple usage. Okay, this is a very innocent use, just to see some code. And as you can see, one thing you should note from this is we are obtaining from the response a push builder, and we're only executing this code if push is supported. So the client can actually specify, I do not support push, I do not support server push, and that will be reflected here, so you don't waste time executing code pushing resources that the client simply is not going to accept. So a slightly more intelligent way of implementing this is not to amend your service, but to actually implement it as a filter. Now this allows you to implement it as a cross-cutting concern, so that all your requests that come into your application are intercepted, analyzed, and the resources are sent back in a push manner. This is a very simple example. You wouldn't necessarily write it like this. What you ought to do is have a look at how Jetty has implemented this. Jetty has done a very good job of implementing a push cache filter, which has far more sophisticated code than this very simple code that I have here. This is purely for demonstration to show you that you can use a filter to implement this as a cross-cutting concern. So obviously JSF is the natural place where this will take prominence. JSF has a lot of resources that it needs to deliver to the client. And one thing that I want to say here, and the only thing I'm going to say here, is that JSF users get server push for free. If you're using JSF and you upgrade to JSF in Java Enterprise 8, you get it for free, you don't need to do anything. Okay? You get server push out of the box, you don't need to make any changes whatsoever. Okay? How that is implemented is kind of beyond the scope, but they're available free for you out of the box. So, like I said before, the client can set whether it wants to enable or disable server push, so the client still has control over what's going on. The server is not just pushing any old resource to the client. The client can specify it doesn't want to accept any kind of resources, but also can reject individual resources. by sending an RST stream, by rejecting individual resources, perhaps because the resources are already cached on the client. And the server is obligated to respect that request. So this is perfectly backward compatible. You don't need to make really any changes on what you're currently doing. The only thing you might want to do is to do a little bit of rework in order to take advantage of Servlet Push, and that's normally probably only really going to be implementing a filter, for example. Okay, if you use Jetty, you get it for free. It's already there. But you might also want to consider reworking your front end, because in your front end you've got a lot of hacks. Let's put it that way. A lot of hacks, a lot of workarounds that have had to be put in there in order to make HTTP 1.1 actually work the way you want it to work. You don't need them anymore. You can take them out. Okay? You can take them out, and you can be assured that you'll get really good performance by doing so, because you're going to be taking full advantage of all the new features of HTTP 2. Most of them are just available for free out of the box. Very little work that needs to be done on your behalf. Just upgrade the servers. So yeah, like I said, JSON developers get it for free. Who supports it? Any server that is currently attempting to implement anything for Enterprise 8. So Glassfish 5 nightly builds are currently supporting it. Pyara 5 has a Java EE8 branch. Jetty has a stable 9 version. This has the push cache filter and push builder already implemented, so just no need to change when using Jetty. Wildfly again has an initial push builder available. Tomcat 9 has a push builder in the JavaX.service.http package. You'll need to implement your own filter in order to make it work. And Netty as well takes full advantage of HTTP 2. So where are we with regards to the current status? Well, currently Servlet spec is in public review. This is the last stage, and it's going to go through to the public review ballot on the 23rd, which lasts until the 5th of June. So we're pretty much there, okay? Should be done hopefully by Java 1. That's really an overriding objective. If you want to follow any of the issues, you could do so on the GitHub. This is now the official place to track issues. This has just been migrated over to GitHub. The JCP specification is here. It's JSR 369. So go download that, have a good read. It's not a very big specification, but it's a very interesting specification, so I strongly recommend that. And you can follow their Twitter if you want to. Extra bits, what I want to do quickly is skip over this slide, which actually, these are very interesting links, which if you go to these links, they will really demonstrate to you the power in the performance benefits of HTTP 2. And finally, and this is going to be very useful, these are 2 free ebooks that explain in explicit detail all about HTTP 2. Okay, these are excellent books. These are constantly distributed. Anybody who talks about HTTP 2 will mention these 2 books. They're well worth downloading. And there's a frequently asked questions as well, which also covers some common questions. I don't think we have time for questions and answers, but you can ask me.